Lecture 7, Forecasting Supreme Court Decisions, Part 3. So now we want to have the card model in R. So here we assume that we have imported our dataset to R, into R, and also we have split the dataset into train, and test set. So the Stevens train is our train data set. Okay, so let's call our model as Stevens tree here. So the R part is the recursive partitioning actually. So it's a package in R which can be used for classification and regression tree model. Okay, so after that, same as linear and logistic regression model, first we have the dependent variable, which is reversed here under the tilde sign, and after that we have the list of independent variables separated by the plus sign. Okay, at the end we should mention the method for the R part function here. So the method can take two values of class and ANOVA. So class mentions the classification, which will be the cart method, and ANOVA can be used for regression. Okay, and so our data actually here is a Stevens train, and the min bucket equals 25. So the min bucket actually is the minimum number of observations in each bucket. So it's a control parameter, right? Control parameter for the size of the tree. So here, for example, we decided to consider at least 25 observations at each bucket. Okay. So after building the tree by the command of PRP and then Stevens tree, we can have the tree here. So see here we have the tree. The first independent variable for a split is the lower chord. So the lower chord equals liberal, yes on the left side, no on the right side. Okay, and then the second split is based on the variable of circuit. Okay, on the left side for the yes, and respondent on the right side for the no. And again, respondent here for the no on the circuit, and again circuit here for the yes for respondent. So as you see here, we are considering the circuit and then respondent and then the lower chord, right? These three independent variables are considered for the split. That means these three variables are the significant ones. So yeah, as we mentioned, only the significant variables are used for a split in card. So here we haven't used the issue, petitioner, and unconst, which are insignificant in our model. Okay. So in card, the value of the min bucket can affect the model's accuracy on the out of sample data set. So here one question arises is how should we set this parameter? Okay, so maybe we can say one way is to select the value that gives the best testing set accuracy. Okay, so can this approach be right? Actually, no, because the test set can only be used for the evaluation purpose. We cannot use the test set to tune or adjust our model. Any adjustment and tuning should be done by the train data set. So the test set should be only considered for the evaluation purpose, and so it cannot be considered for tuning our model. Okay. So one way to properly select a parameter's value is to use k-fold cross-validation. Okay, so what's k-fold cross-validation? Here we consider our training data set and then we split our training data set into k pieces. This is why we call it as k folds. So k pieces or k folds, and then we use k minus 1 folds to estimate a model, and then the model will be tested on the remaining one fold, which is actually called here a validation set for each candidate parameter value. Okay, so we repeat this approach for each of the k folds. So at the end, for each candidate parameter value, we can calculate the average accuracy over the k folds, and that will be our measure to see which candidate parameter value is the best. Okay, so let's have an example here. Let's assume that we have 5 folds. Okay, so in this set, we are using the folds of 1, 2, 4, and 5 in order to estimate fold 3. Or here, we're using the folds 1, 2, 3, and 5 to estimate fold 4, right? And also here, fold 1, 2, 3, and 4 are used to estimate fold 5. So by doing this for all k folds, we can calculate the average accuracy, and then by having that measure, we can see which candidate parameter value is the best. Okay, for example, here let's we have this curve as the accuracy of the fold 1 over different values of our parameter. So that means, so we have used, let's say, other folds except fold 1 to estimate fold 1 by a certain value of the parameter, and then we are doing this for all possible values for the parameter value, and then by having that we can plot this curve. Okay, so we can do this for all folds, I mean for k folds, and at the end we can calculate the average, right? So the black one here, the black one is the average over the 5 folds, and then by having this average, we can see what's the best level for our parameter. So by considering the maximum level of the accuracy, I mean the average accuracy here, we see that the value of 6 is the best value of our parameter. Okay. So let's see how cross-validation works in R. So in R, we can have the CP measure. CP actually is the complexity parameter, and it's a measure for trade-off between the model complexity and the accuracy on the training set. Okay, so the smaller CP leads to a bigger tree. Okay, so we may say, okay, the smaller the CP is the better, but maybe we have the overfit issue here. So we should be careful about the smaller values of CP, but in general, the smaller value for CP is the better if we don't have the issue of overfit. Okay. So here in R, by the command of print CP and the Stevens tree, we can have the value, I mean the analysis over the cross validation. So here usually by default R considers 10 folds. So these results here are based on 10 folds, the average over 10 folds. Okay. And as you see here, we have the number of S-bullets, 0, 1, 3, and 5. And here we have the CP here. This is the CP. Let me show with a different color here. So yeah, this is the CP value, and then the number of S-bullets, and then relative error, rel error or relative error, and then X error, and X standard error. Okay, so the relative error is 1 minus R square, which is the root mean square error. So this is actually the error for predictions of the data that were used to estimate the model, okay, on trained data set. And the X error is the cross-validation errors, or the average error over the K folds. Here is over, it's over 10 folds, okay? Yeah, generated by R part built-in cross-validation, okay? And XSTD, or standard error over the cross validation, okay? So if we consider this result here, we see that the last row, which corresponds to 5 splits, has a smaller error, relative error, which is 0.633. And so, yeah, we can consider this as the best split number, okay? After building a card model in R, we need to plot the tree and see if all decision rules make sense. So we may see some strange rules sometimes, and if we see some rules are strange, then we may need to do more investigation, okay? And the independent variables that used to build the tree are the most important ones. So if you see some of the independent variables are not appearing in the tree, that means those variables are not important enough, okay? And at the end, we can assess the accuracy of our model over the test data set, okay? So if we have category called outcome, uh, we can build a classification metrics like the logistic regression model and see what's the accuracy. Or if we have a continuous outcome, we can consider R squared for the accuracy, or the performance measure of the model, okay? So let's wrap up the card model. We can say the most important independent variables will appear at the top of the tree, okay? And the card model usually works best on large amount of data. So for smaller data sets, we have a variation of card, which is called a random forest. So random forest is a variation of card, and it's designed to work better on smaller data sets. So in the next part, we will have the random forest method. Okay, thank you.